Every year, the global dairy industry produces hundreds of millions of tons of raw liquid milk. To store and transport even a fraction of this immense volume, it has to be stabilized before it spoils. The problem is biological. Raw milk is roughly 87% water. That makes it incredibly heavy, expensive to move, and a perfect breeding ground for bacterial growth. The most effective way to eliminate those logistical bottlenecks is total dehydration, stripping the water away entirely to produce a shelf-stable powder. But removing that water requires triggering a physical phase change from liquid to gas. In an industrial setting, that means injecting massive amounts of thermal energy into the system to boil the moisture off. Applying extreme heat to complex organic material comes with a severe cost. High temperatures rapidly denature fragile proteins and caramelize sugars, risking the destruction of the very food matrix you are trying to preserve. To navigate this, engineers generally rely on one of two industrial dehydration methods: drum drying or spray drying. In a drum dryer, milk hits a 150-degree metal surface. The heat boils the water, but severely burns the product. In a spray dryer, milk enters 200-degree air, yet emerges as pristine, unburned powder. Why does 150 degrees destroy milk, while 200 protects it? The numbers on the temperature gauges alone cannot answer this. To resolve the paradox, we have to tear down the specific heat transfer mechanisms driving each machine. This is a set of engineering diagrams showing the cross-sections of single, double, and twin drum dryers. In this process, concentrated liquid milk is fed continuously onto the exterior of these revolving drums. The machine applies a microscopic film of liquid, usually less than 2 millimeters thick, directly onto the outer metal. Inside those cylinders, pressurized steam acts as the heat source. That internal steam drives the external metal surface to temperatures well above 150 degrees Celsius. The heat is so intense that the moisture flashes off in less than a single revolution of the drum. A mechanical scraper, known as a doctor blade, then forcefully peels the dried sheet off the metal. The mechanism driving this entire system is thermal conduction. The heat energy transfers through direct physical contact from the solid metal drum straight into the thin liquid film. Because the milk remains locked in physical contact with the metal, the temperature of the drying product rapidly converges with that 150-degree surface. That intense thermal load causes the milk proteins to rapidly denature and triggers Maillard browning reactions across the sugars. The drum dryer successfully dehydrates the milk, but its reliance on brute force thermal conduction inevitably sacrifices the chemical integrity of the food. This schematic shows an alternative system engineered to bypass that conductive trap: the spray drying tower. Instead of laying milk onto hot metal, liquid milk is pumped under extreme pressure up to the very top of the main drying chamber, where it is forced through an atomizer. That single continuous stream of liquid is violently shattered, exploding into hundreds of thousands of microscopic droplets suspended in midair. Breaking the liquid down to this microscopic scale exponentially increases the total surface area to volume ratio of the milk. These droplets are then injected downward into the massive chamber alongside a continuous, convective flow of air heated up to 200 degrees Celsius. The liquid droplets are now completely enveloped in an environment 50 degrees hotter than the drum dryer that burned them. So how do these particles survive a 200-degree convective inferno? The survival of the milk relies entirely on a physical law known as the wet bulb effect. If we measure the environment inside the tower, the inlet air sits at 200 degrees Celsius. The exit air drops down to 120 degrees. But the temperature of the drying particle itself remains locked firmly below 80 degrees. As long as that droplet contains free water, the immense thermal energy from the hot air doesn't heat up the solid milk matter. Instead, that energy is entirely consumed by the phase change of the water evaporating. Physicists define this specific mechanism of energy consumption as the latent heat of vaporization. The heat from the 200-degree air is doing physical work. It uses its energy to break the molecular bonds of the liquid water, turning it into gas. Because the energy is spent on this conversion, it does not raise the sensible temperature of the actual milk proteins and sugars. But there is a strict window of vulnerability. This thermodynamic protection only lasts as long as there is free water evaporating off the surface. Once the droplet hits around 3% moisture, evaporation slows down. At that precise moment, the particle's temperature would spike to match the 200-degree air, except the system's massive airflow sweeps the particle completely out of the high heat zone before that can happen. Evaporative cooling acts as an invisible thermal shield. It allows engineers to blast the milk with ultra-high temperatures to achieve rapid dehydration, without imparting any high-temperature damage to the food itself. We can verify this process by looking directly at the end product. This is a photomicrograph of spray-dried whole milk. Notice the resulting geometry. The powder consists entirely of distinct, highly porous microscopic spheres. Because the atomized droplet dehydrated while suspended in midair through rapid multi-directional evaporation, it permanently locked into this perfect spherical shape. Contrast this with the output of a drum dryer, which yields rigid, flat flakes that have been sheared off a metal cylinder. This spherical geometry serves an incredibly practical chemical purpose. The porous structure gives the spray-dried particle immense surface area, allowing it to rapidly wet and dissolve when reintroduced to water. That highly soluble geometry, combined with a completely unburned chemical profile, makes spray drying the only viable method for producing premium, beverage-quality milk powder. Looking at both dehydration systems, the engineering lessons become clear. Drum drying relies on thermal conduction. It guarantees water removal through sheer mechanical efficiency, but to get there, it surrenders control over the molecular integrity of the food. Spray drying takes an entirely different approach. It uses precise fluid dynamics and high-pressure atomization to manipulate the surrounding environment. The spray dryer succeeds because it completely uncouples the extreme heat of the drying medium from the internal temperature of the food. By mastering the invisible physics of the wet bulb effect, engineers took a highly perishable biological liquid and permanently transformed it into a stable, globally distributable commodity.